Wow. Wow. Hello, hello, hello. Wow, incredible. Martian Robonaut. The 1/2 Raider. I remember correctly. 1/2 Raider. Algebraically challenged. Hey, what's going on? Math in the morning. Great. Let's hope this lecture goes smoothly. I think it's going to be a rough one. Oh, gangsta. Thanks for following. That's right, algebraically challenged. That's right. We've signed up for this, I guess. I suppose. Oh, rocket science. Well, I feel like you should probably go back and work on the rocket science. I mean, the stakes might be a little bit higher. You know, people's lives depend on that. Not sure people's lives depend on Lagrange, actually. I'm not sure about that either. I think your bank accounts might depend on abstract algebra. Security. In fact, I'm pretty sure that's the case. Okay, let's see. How many people showed up to class today? Let's see. Let's do a poll. Here's a little quick poll. Got yourself a little poll going. Okay. Oh, hello, Jeeves. Oh. Officer. Yeah, that's right. Oh, that's a typo from one of my students. One of my former students typed that in chat, and I made fun of them for it. I mean, I'll be honest. And then I sort of memorialized them by putting them on the starting soon screen. You got the initials wrong. Yeah. But hey, what's going on? Hey. All right, so I gotta start now. I gotta start. Let's go, class. Hopefully you're here. You're not on Discord, but hopefully you're here. Okay, so again, I have to remind you, I have a 45-minute lecture, so I won't be able to look at chat during the lecture. I'll focus on chat afterwards for for about 15 minutes. Oh yeah, the cool intro music's gone, but no worries. Wait, you're saying there was no music playing? That's weird. Okay, wait, hold on. See if okay, here's some music while I begin the class. There was, but then the lesson started. Yeah, well, yeah. That's how that works. Smash time. That's how that works. It's cause and effect. Okay, let's go. All right. So I have a 3-part structure going on here, 3 separate parallel lines. And so let's dive right in. So I wanted to show you the power of Lagrange's theorem combined with this one new tool. So that's what I'm going to start with, number 1, and then we'll finish Cayley's theorem, number 2, and then we'll go back and play around in the alternating group because it's not at all clear. Oh, this is my scratch work. Don't mind that. It's not at all clear that the alternating groups should exist when you first see these things. Okay, so the poll has ended, and yes, so yeah, okay, it was a predictable result. Let's not talk about it. Okay, here we go. Sample consequence of Lagrange, our first sort of, you can witness the power of Lagrange's theorem. So what was the theorem we're trying to prove? Let P be an odd prime. I mean, the P equals 2 case is a separate, easy exercise, so we're not going to deal with that. But let P be an odd prime, then any group of order 2 times P is isomorphic to Z, the cyclic group of order 2P, or the dihedral group, the symmetries of a p-sided perfect shape, perfect p-gon, okay, so to speak. So we know exactly which groups you're looking at if you're looking at a group of order 2p. Awesome. This is a spectacular news. But how the heck do you prove this? How on earth does this get proven? Okay, so the main tool we're going to use, the tools. You use Lagrange, which I'll just remind you in quotes. And then you use the HK trick. Let me remind you what the HK trick is. If H and K are 2 subgroups, finite subgroups. Then the number of elements in the set of all multiplications H times K, this is a subset of the group G, not a subgroup necessarily, just a subset. The number of elements of type H times K is the size of H times the size of K divided by the size of the intersection. This is kind of a wonderful tool. All right, this little HK trick. All right, let's see. Let's dive in and reason our way through this theorem. Okay, this great classification theorem that we have apparently we're on the verge of witnessing. Okay, So what we know is, let me begin that. So suppose G is a group that has order 2p as hypothesized. Okay. If H and K are parallel, then you would be dividing by 0. Yeah, you're in the wrong class. Wrong class, Smash Time. Yeah. Okay. So suppose you should go to the classroom next door. I think you got the classroom wrong. That's the geometry class. Okay, so suppose G is has 2p, size 2p. And now there are 3 cases. There are some number of cases. Okay, case 1. Every element that's not every non-trivial element, non-identity, has order 2. That's possible. That order is possible because 2 divides 2p. We don't know that that it must be the case that there's an element of order 2. We will eventually prove such a beautiful result. But here's a possibility. Every element you ever pick that's not the identity has order 2. But then, by a homework exercise, the group would be abelian. Okay, so this is one situation. And now what I'll do is, okay, so now pick 2 non-trivial elements in this group. Different, yeah, different. Non-trivial elements, distinct. So different means distinct. Non-trivial elements. So then, if you do this, the set identity A, B, and AB, this set forms a subgroup. You have to check this. Look, is A times A in this thing? Yes, because everything has order 2. Are inverses in this thing? Yes, because everything is its own inverse, because everything has order 2. Oh, is A times AB in this? Well, yeah, A times A is identity, so this is A times AB is just B. So yeah, this thing is a 4-element subgroup. This is a 4-element subgroup. This violates Lagrange's theorem, though. Because 4 doesn't divide 2 times p. P is an odd prime. Okay, so case 1 doesn't happen. Okay, wonderful. All right, I hope some of you are seeing this for the first time, so you witness how great Lagrange's theorem is, and you feel the joy. Okay, let's do a stupid case. Case 2. Case 2. Case 2 is that some element in G has order 2p. What are the possible orders? They have to divide the order of the group by Lagrange's theorem. So 2p and 2p are the possible orders. We're sort of going down that case, those cases. Okay, so now look. So some element in G has order 2 times p. All right. Okay, so now let's think about that. Let's think about that, folks. Okay. So oh, this is stupid. Yeah, this is silly. It immediately implies that G is a cyclic group. hence isomorphic to Z mod 2PZ. So that is the branch that produces the possibility, one of the two possibilities stated in our original theorem. So that's how you can get case. That's how you get the first situation. All right. So now we look at case 3. So case 2 is dealt with. It's good. It's possible. So case 3. The case 3 is that no element has order 2p. Okay? And we know that therefore there has to be an element of order p. Because everything can't have order 2 by case 1. Case 1 couldn't happen. Then there must be an element of order p. Let's call it A. Okay. So now I'm gonna do the following thing. I'm gonna draw up. I'm gonna evoke the cyclic subgroup generated by A. So let H denote the cyclic subgroup A, which I want to remind you is identity A squared up to A to the P minus first power, because A to the P is identity again. So it's this P element subgroup that you get. Okay? And now pick any element B that's not in this subgroup. Right? Pick any element that's not in this subgroup. Here's the claim. Claim is that B cannot have order P. Let's draw this claim in different color, purple. All right, so let me draw pictures. Here's our group G. Here's cyclic subgroup A. Cyclic subgroup of A. And what I did was, notice how many elements are left. There's exactly P elements left. And I chose B in here, in this, the remaining part. In a coset, the remaining part has to be a coset of the set of their subgroup H, a left coset, for example. Okay, so the claim is B cannot have order P. All right, so why is that true? Why? If B had order P, then letting K equal this subgroup, the cyclic subgroup generated by B, we would have that the number of elements which are of the form H times and a power of A times a power of B, that's H times K, would equal the size of H times the size of K divided by the intersection. This is just this is our HK tool. HK tool comes in. But what we need to understand is the following: that in this tool, the denominator here has to be 1. this denominator must be 1 because this is a subgroup of H and of K. This is a subgroup of H, and so its order is either 1, which is what we're claiming, or the other extreme is its order is P by Lagrange's theorem. But if its order is P, then H and K would be the same subgroup, violating me choosing an element outside of H. So the fact that I chose an element outside of H guarantees that H intersect K must be the trivial group. So this must be 1. Again, there's a little use of a Lagrange theorem there. A little bit of a flavor there. Okay, so this product set, this set of products would have size H times K, which is P times P, which is bigger than 2P. And I should write this in red because that's a terrible conclusion. You can't have a subset bigger than the set. Should the denominator be written H and K instead of H and K? No. Oh, yeah. Yes, absolutely. H intersect K. 100%. Did I make that mistake here too? Yeah, good. Thank you, Sloth. Absolutely. The size of the intersection subgroup. 100%. Yes, good. Thank you. Great. And the point is the intersection has to be trivial because it has to either be size 1 or size P. Can't be P. Fantastic. Great. So, what we conclude, conclude. Every element outside of H must have order 2. Every element outside of H must have order 2. Why? The element can't have order 2P because that's what we're pretending in case 3. No element has order 2P. The element can't have order P thanks to the HK trick. And so there's only one option for the elements outside of H. They must have order 2. And now, once you know this, the group is frozen. The group structure is uniquely determined. Group multiplication table. Is uniquely determined. For instance, Yes, odd prime. Yeah, you can classify the groups of order 4 very easily. In fact, just by a Sudoku type, what can the multiplication table be? The answer will be there are two such groups, Z mod 4Z and Z2 cross Z2. Z mod 2 cross Z mod 2. There are two groups of order 4 up to isomorphism. So that one, just side exercise. Okay, so once you know this, the group multiplication is uniquely determined. For example, if you take A times B A times B is still not an element in H, because that would imply that B is in H. So A times B is in this coset. It's outside of H. A times B, therefore, squared is the identity. We know that. And so what this tells you is that A times B is what is it? What does this tell you? Hold on. A times B times A times B. Right, equals E. Let me do some math real fast. So A times B times A is B inverse, which is B, because B has order 2. And therefore, I hope I'm not going in circles here, but A times B is therefore B times A inverse. So you, for example, you get this conclusion. If you want to multiply A times B, you can swap the order, but then A gets inverted. That's part of the group structure that has to be the case here. Okay? And why did I write this? Because once you know this rule, you can multiply all expressions involving A and B. So once you know this rule, then like A squared B times A cubed B times etc. Why didn't I write B squared or B cubed? Because I can just collapse those. B squared is the identity. Anything outside of H squares to the identity. The point is to see that this freezes the group structure. What is this total end result? Combine it, use this multiple times and you'd get B times A minus 2 times A cubed times B. I'm just doing a example. And then do it again, etc. You can move all the B's to one side and all the A's to the other side. And it sort of equals some power of A times a B. Move all the A's to one side and move all the B's to the other side. And then you'll figure out how to multiply all the elements in the left coset or right coset, whatever I'm doing, with each other. And that freezes the group structure. So the multiplication table is determined. And now you can produce a homomorphism. We'll call it F. From the dihedral group to G. And what's the rule of this homomorphism? It is to send a rotation, R 2 pi over P. Rotation by order 2 pi over P. Send that to A. And then flip across x-axis. Send that to B. And this will be a homomorphism because the multiplication structure relationships between R, powers of R, and F is the same as the multiplication structure between powers of A and B. This is a homomorphism, and this map is bijection. Is a bijection. Okay, so the key is to say that the group structure in this case is frozen to be one particular multiplication table. And that particular multiplication table is the same table that you'd see if you squint at the dihedral group. But what you want to what I want to emphasize is how these kinds of, this HK tool can be combined with Lagrange's theorem to sort of navigate a bunch of cases. That's the thing you want to learn from this example. If you're seeing this kind of math for the first time, I think it's really cool how mathematicians have developed these little simple but highly effective counting arguments, essentially. And by putting them together in different combinations, you can just barely squeeze by to get beautiful classification results, like any group of order 2 times an odd prime is one of 2 groups up to isomorphism. Cyclic or dihedral. Fantastic. So that concludes my take on the first sample consequence of seeing Lagrange's theorem in action. I hope you enjoyed that. It's really fun to see how such an innocent statement can be like amplified to such great effect, and you'll see it manifest so many more times as we go further into group theory. Okay, now I got to finish Cayley's theorem, so I'm going to move on. Drastic change of topic. Cayley's theorem. So save your questions for afterwards, and thank you, Sloth, for making sure I don't make any stupid mistakes. Very important. Okay, so Cayley's theorem. Every finite group is isomorphic to a subgroup of some symmetric group. Let's call it permutation group. Okay? All right. So the idea is this. The idea is a tongue twister. So let G be a finite group. And now you're going to define a homomorphism. Now, last class I messed up. I made a classic mistake, and I want maybe in the question time someone can see exactly how my initial my proposed homomorphism, why it's got a little problem. It's a classic mistake I made. So learn from it. So let G be a finite group. So I construct the following homomorphism. The translate by G homomorphism. It is a function. It is a function from the group G, takes an element of the group, and produces a permutation of the set, which is the group. A scrambling of that set. So what is that permutation? For each element in the group, of course, it produces something called T. I'm going to write it T sub G to not confuse notation. So what is T sub G for an element of the group? T sub G is a permutation of the group. So it is a bijection of the group with itself. What is the name of that bijection? T sub G of an element is H times G on the right side. Multiply by G on the right side. I don't want to use H here for later. I'll use just X. If I have an element in the group X, this permutation is multiply X on the right by G. Okay? Why is T sub G of X a permutation? So I'll leave that as an exercise. Prove using group axioms that T sub G is indeed both injective and bijective. is injective and surjective. Okay? Let me say it another way. What this exercise is saying is when you write out the multiplication table in a group, the column labeled G is always just the elements in the column are all is just a scrambling of the set G of the group itself. In every column, every element occurs exactly once. That's what this exercise is. Okay, so you go and see why that's the same exercise. Okay, so in summary, tongue twister. In summary, for every element in the group, I have produced a scrambling of that group, a permutation of the group. Okay? And now the point is that this function capital T is a homomorphism. Okay, so the claims that you have to check, the claim is capital T is a group homomorphism. Now, what is the group structure on permutation of G? It is composition of functions. Composition of permutations. Same, it's always the same when you're looking at permutations of a set. The group structure. It is just do one, then the other. Okay, so T is a group homomorphism. In other words, T applied to a product, G times H, is T of G, T of H. It is that multiplication. That multiplying first produces the same effect as do the first, then the second. So this is how we're going to state this. Okay, it's a group homomorphism like that. Okay. So why? So check this. So verify. Let's see what the left-hand side does to an element X. By definition, the translation corresponding to an element, in this case the element's called G times H, is you take this input and hit it on the right by GH. This is by definition of T sub whatever. Okay? Now I'll write this as X times G times H. You can do this because of AS, right? Okay? And now you look at this, and this is the translation by H of the element X times G. That's what T sub H does. It translates on the right, multiplies on the right by the element. But this is then, again, this, which is first do T of G, then do T of H. Okay? And so in this way, the mapping from the group itself to a set of permutations, permutation on the set called underlying the group, this mapping is a homomorphism, is a group homomorphism. Okay? So that's great. But now we need to check that this homomorphism is a one-to-one, and then it will be bijection onto its image. So now must check. Is T one-to-one? onto its image. If it is, then T is a bijection with its image, and therefore we have seen an isomorphic copy, namely the image of G, an isomorphic copy of G inside of a permutation group. That's the claim that Cayley is making. Okay, so let's check injectivity. Now, to check whether a homomorphism is injective, not a random function, but a homomorphism. To check whether a homomorphism is injective, it is enough to prove that the kernel is trivial. We proved this a couple days ago. I don't know. So let's look at the kernel of right translation homomorphism, T. So what is the kernel of this homomorphism? Well, by definition, kernel is the set of elements in the group such that T of that element, which we've called T sub G, because I don't want too many parentheses in the mathematics. This thing is the identity in permutation group, but that's the identity function. Okay? So it's those elements which induce the identity on under right translation. Okay, but if T sub G is identity, then T sub G of the element E would be identity of the element E, but identity function takes an element and just spits out itself. So on the one hand, T sub G of the identity would be the identity, but then on the other hand, by definition, T sub G of the identity is E times G. You multiply on the right by this element. And so we'd get E times G equals E. But now group, that just means G equals identity. Done. Therefore, this kernel consists of simply the identity element. It's trivial. And therefore, T is injective, and therefore T is an isomorphism onto its image. Not onto the permutation group. We're not claiming that the map is a isomorphism surjects onto the permutation group. No, just the map to its image. The image of a homomorphism is a subgroup. So the map from G to its image is injective and therefore bijective onto its image, not onto the whole permutation group. And this concludes. Oh, thank you, Nam Sane, NHL, Fomaborn, Gangsta, Sniper, Zenjamin. Thank you all. All right. So T is an isomorphism onto its image, and so Cayley's theorem follows. Okay, so what's the conclusion? Why is Cayley's theorem interesting? Okay, it's used not so much. Okay, that's the first thing I'll say. Don't confuse this Cayley's theorem with the one from linear algebra, which is used all the time, that a matrix obeys its characteristic polynomial. don't or satisfies its characteristic polynomial. That one is very important, but this one kind of niche. However, what's important is the significance of it philosophically. Some students think that the groups that arise as permutations and concrete scramblings of a shape or an object or a set, that those are somehow more important than the full abstract world of all finite groups. Well, you are hallucinating, because every abstract conceivable finite group manifests in some way, not very explicitly usually, but it manifests in some way as a subgroup of one of those groups that you actually believe in. You know, groups of scramblings or Rubik's Cube scrambling things around, you know? Yeah, every finite group is a subgroup of one of those. Is meaning is isomorphic to, is under a homomorphism, is indistinguishable with a subgroup of some permutation group. The permutation group could be enormous. Could be S 1 trillion, but it's in one of those that you seem to prefer. Okay, that's the importance of Cayley's theorem. It's kind of psychological. All right. So last now, in my last 3 minutes. Okay. Hello. Okay, so last 3 minutes, we need to get out. We're in the clouds, right? We're in the clouds right now. We're in the clouds. Here, we are here. So we need to come back to Earth. Come back here. Come here. And that is, let's play around in the alternating groups. Let's get more and more comfortable with the alternating group. I will go over now, over time. Okay, so I definitely know that, just from experience, I know that there are people in the chat who think that the alternating group is some obvious subgroup of Sn. And, you know, students, the 5 of you who are in the class, you should eventually get to the point where you also feel that it's so obvious. However, you should never forget the origins, what it was like when you first saw the object, because then you'll appreciate math. It'll feel more joyous every time the object comes up again. Look, it is not at all obvious that there is a notion of sign of a permutation. It is not at all initially obvious. That permutations have a sign attached to them. In other words, that there's a systematic way of labeling a scrambling as even or as odd. Okay? Now, the thing is, the definition of the sign is, quote, obvious from certain points of view. So here's one point of view where the definition, where the concept of sign becomes obvious. Okay, so here is one way. I showed you one way last time where you look at how a permutation changes the discriminant function. This is one of the historically first ways that people witnessed that there was some notion of sign of a permutation. Okay, evenness and oddness. So here's another way to see that permutations should have some even or odd classification. among them. There's even ones and there's odd ones. Here is an obvious way to get to a sign, to the notion of sign. Or evenness, even oddness. Okay? Prutz, that's exactly right. But now you have to ask. Prutz. Yes, Prutz, the determinant of permutation matrix, exactly. But in all of these, there is non-trivial mathematics buried. It's secretly smuggled in. Let me show you the one that you just mentioned. Let me just show you the one that you just mentioned. Here is an, quote, obvious way to get the notion of evenness and oddness. Okay. For each permutation, in Sn, okay, so sigma, for each permutation in Sn, you can create what's called the permutation matrix. Now this is the matrix. This is the matrix. So if you fix the standard bases, E1 is 1 0 0 0 0, E2 is 0 1, En, n is the same n that we're talking about. In terms of the standard basis, this permutation matrix of sigma, the permutation we began with, is the matrix whose ith column is E of sigma I. In other words, the permutation sigma scrambles the symbols 1 through n. It sends 1 to the third one. 1 to 3, for example. Okay. Stick the third basis vector in the first column, because 3 was the output of 1. Maybe the permutation sent 2 to 7. Stick column 6, basis 7 in the second column, etc. You create a matrix that has bunches of zeros and ones. There's only 1 1 in every row and column. And these are called the permutation matrices because they encode permutations in the way I just described, or in the way that's written like this. Okay? So, the first claim is that this assignment, sigma goes to permutation matrix of sigma, is a group homomorphism. From Sn to GLNR, to the group of matrices, n by n invertible matrices. That's it. First of all, that's the first claim. It preserves the multiplication structure on both sides. And then, once you know this, now you need a second fact. And this is where there's a smuggling. Both of these have a little bit of smuggling, but the second one is where smuggling comes in. The determinant map is a homomorphism. I've said this before, and maybe you saw it for 2 by 2 matrices, but you need to make sure you have to know it for n by n matrices. Okay, so the determinant is a homomorphism. Okay? And so you can compose two homomorphisms. This is the homomorphism called permutation matrix. And then determinant. This is therefore a homomorphism. And if you remember how to compute a determinant, you'll find that this homomorphism, its image, lies in the subgroup plus minus 1. The image of this homomorphism is the set plus and minus 1, this subgroup. The plus minus 1 subgroup of the multiplicative group of R. Okay? And so what is AN? What is AN? AN is the kernel of this plus minus 1 homomorphism. But you have to smuggle in something at some point. In this case, it is that there's this magical thing called determinant, and that it's a homomorphism. So that's if you permute the basis evenly, you'll have the same images of things, and if you permute it oddly, you will have mirrored images. Right? Prutz, that's correct. Except, what does mirror mean in R10? You then have to tell them what that means without being circular in your explanation. You're going to say there's a thing called orientation, and then that certain transformations keep the orientation the same, but you're going in circles at that point. Yeah, so it's very non-trivial, actually. There's like a certain amount of non-trivialness that's inescapable when trying to explain to a person for the first time that there's a notion of there's a notion of sign, of evenness and oddness, of positive 1 determinant and negative 1 determinant attached to a permutation in the first place. Okay, there's a inescapable amount of non-trivial mathematics involved in that. So students, the 5 of you who are learning for the first time, do not listen to the trolls who say, it's just the sign. They don't understand what went on when they don't understand. They have a huge gap in their witnessing of the sequence of logical events. Okay? It's not just the sign. Yes, it is afterwards. But do you know where the sign comes from? And so, in office hours, we will explore this concept of sign more and more. And we'll get a handle for which permutations are even and which ones are odd. There's office hours at 5 p.m. today. So let me say that in the Discord. Important office hours. Important meaning I assume the students probably want it. You should ask your probably very crucial questions. I will also talk about the alternating group. Okay, so that's for my students especially. A very important office hours today where I'll start multiplying permutations. We'll look at them, and then we'll actually witness correctly, thoroughly, that there's a even and odd conspiracy in the world of permutations, and the alternating group consists of the even permutations, and it forms it forms a subgroup of size 1/2 of the symmetric group. I might also put on the neuroimaging to show you a visual representation of the group A4, the 4th alternating group. So yeah, office hours, very important. Be there. Okay. Hey, hold up. I didn't sign up for this. Very good. Make things as simple as possible, but no simpler. Great. Yeah. Very good. 6 students. 5. I have 5 students in this class. Oh, Kappa Klaus. Cayley Hamilton. You're right. You're right. I forgot the Hamilton. You're absolutely right. Cayley Hamilton is the one that matrix obeys its characteristic polynomial. That's right. Absolutely. Is it related to even an odd number of simple permutations required to get the given permutation? Yes, Prutz. But once again, why is that even a well-defined notion? Why is it that when you express a permutation as a product of transpositions, that the number of different ways of expressing it have the same parity? That's not obvious at all. That's why should there be a parity conspiracy in different ways of representing an element as a product of transpositions? Again, you can't escape this non-trivial there's a conservation of work in this field, and each time you do it, you might come up with a very slick visual way to show this, but that is content. That's not obvious. The more slick your reasoning, less it's not obvious anymore. So in office hours, I will go into that. Where does evenness and oddness come from, and why is it called even and odd? And what's an example of odd and even permutations which have different shapes, cyclotypes, and so on? That's what we'll do. Okay. No, not really, but sort of. Meaning, I suspect that some of you are lacking in seeing me do are wanting to more examples, so I might as well do them. Do them as soon as possible, meaning in today's office hours. Sloth, are you here? Are you in class? Maybe you're not in class. Maybe 2 people are in class, I guess. Okay, so yeah, go. You probably have other classes, so everyone go to your other classes. I have another class I have to cram for. Partial fractions. I have to learn what those are all over again. So I better get going, folks. Let's see. Do I know the game of 15? Yes, I know the game of 15, and I know its relationship to permutations. Yes, but I mean, I know it because I read it. I mean, I didn't come up with it or anything. None of what I talk about did I come up with. And so, but I try to make it so that people are aware that certain things are not obvious, even though when they grow up, they start to it starts to become second nature. And you go back, this is a point where, why is there an alternating group? Kind of a good question, I think. Then it'll stick with you longer. We A3 free, Shirshak, Amen, brother. We A3 free. I couldn't have said it better. We A3 free. Okay, so Prof Melko. He's on? Okay, Prof Melko, let's go. Let's go raid Prof Melko. And thank you for everyone showing up. All the weird voyeuristic strangers who are just sitting in on my class. That's strange, but thank you. Okay, so Melko, where's Melko? Hey, Melko's not on. Prof Melko. Oh, he is. Yeah, kappa. That's one way to do it. The sort of length function. But again, that the length is well defined. A little bit of a headache, don't you think? That the length is a well-defined concept. Yeah, kappa, but I don't think it's so bad. Like, I'll do it in office hours. I'll demonstrate that there's a... I mean, I only know one way of doing it. And this is the way that I was taught a long time ago. And it's just a proof by induction, so essentially. And it's not that hard. It involves doing 3 calculations, and that's it. So, or maybe 2. I'll deal with it when I get there. But okay. So let's go. Let's go. Prof Melko. Here we go. Go say hi to Prof Melko. Go be, since it's Prof Melko, go be trolls. Yeah? Try to derail whatever lecture he's giving. Just go do that. Usually I tell you to go and respect the person, but it's Prof Melko, right? It's a direct competitor. So make sure you take their whole stream down. Okay, here we go. Start the raid. Here we go. I think the raid is going. Ready? Ready? There's a weird like glitch that happens. If I click this,